Good evening, and welcome to the 9th annual Carnegie Astronomy Public Lecture Series. My name is John Mulcahy. I'm a staff astronomer at Carnegie, and I helped put the series together this year. Our attendance is amazing. This is really quite impressive. We had to shut the gates because there were too many people, so you're lucky you made it. This is really quite impressive. We really appreciate the enthusiasm for everybody coming out. We have a very exciting series this year with covering a large range of topics. We're going to hear about dark energy and dark matter. We're going to hear about galaxies in formation. We have a first for our lecture series. We're going to have a talk on the universe in simulations, an entire talk based on how some astronomers spend time on their computer trying to reproduce the universe. So that should be really interesting. So very great talks. And tonight, one of the most exciting topics in astronomy is, of course, life in the universe. And this might actually be the first, or Alan gave a talk on life in the universe? Maybe, yeah, it's been too many years. I can't remember all of them. Oh, we did have water, that's right, yeah. So anyhow, we're gonna hear about life in the universe, and which you hear about in the news all the time, for better or worse. Maybe Chris will talk about that, I don't know. So let me start by thanking the Huntington for hosting our series again. I want to thank the Hearst Foundation, which provides some support for our series. And I want to thank everybody again for coming out. I have the pleasure of introducing tonight's speaker. Tonight's speaker is Chris Burns. He is a research astronomer at Carnegie. He got his PhD in 2002 at the University of Toronto, where he worked on gravitational lensing, which I don't think we ever had a talk on that. That would be a good, interesting topic.
No way.
No. For the future.
No.
He then came to Carnegie to work on the Carnegie Supernova Project, a project that Wendy Friedman talked about a few years ago, a very large program we're doing at Magellan telescopes to study the size of the universe and dark energy and dark matter and those sorts of topics. So you may remember that. Chris has been very vital in that project. But tonight he decided to talk about something he doesn't work on, which is always a daring move, but he's probably spent a lot of time researching this, and that's life in the universe. So let me help me welcome Chris Burns. And does everybody have their 3D glasses? Yes.
Does anyone need some?
One pair? Okay.
Thanks, John. So first, can you hear me all the way through the room? A little bit louder, maybe? Is that okay? Okay, good. Well, thanks for having me. And yes, I am striking out into the unknown a little bit. I actually spent 4 years at Swarthmore College teaching astronomy to astronomy, physics, and every other kind of student who goes through those doors. Are there any Swarthmore alums tonight here? Yeah, okay, cool, one. So, yeah, you'd be surprised. I mean, I see these guys at Trader Joe's all the time. So this isn't exactly me being completely out of my element, because I actually did have to teach this for 4 years. It was one of the most popular classes we ever had. Completely always, just like tonight, completely full up, and we always had a waiting list. And that's because it's a very, very interesting topic. And it's also a lot of fun to teach because it brings together many different disciplines, not just astronomy, but chemistry, geology, biology, all that stuff. And you kind of have to get to know it in order to teach it. And so I learned a lot when I took this class. Sorry, when I taught the class. But so in some sense, I actually did take the class as well. So my first warning slide. Oh, and by the way, sorry, I see some of you putting your 3D glasses on. There is some 3D content tonight, but it's not the whole lecture, although if you really want to have them on the whole time, that'd be fine. So this is about as close as I get to real biology. So I'm not a biologist. Try and keep that in mind. If there are any biologists in the audience, I apologize right now. I might mess things up a little bit, and feel free to point that out in the questions after the talk. I usually try to stay clear of too many scientific graphs, but there will be a few tonight. And just because picture's worth 1,000 words, graphs are probably worth 2,000 words. So we might see some pie graphs. I think you've probably seen pie graphs before, bar charts, and maybe a couple of graphs like this. And if any of you are sort of nearing the retirement age, you've probably been looking at graphs like this recently, right? Especially ones that kind of go down and then maybe up. Hopefully they're going up. All right, so tonight's topic, life in the universe. So let's start it off. What is life? This is how I started off my class when I taught it. And I would say to my students, all right, what's life? And unfortunately, I can't really give you a really good answer because it's kind of like trying to ask what is water to the Greeks, who didn't have the molecular theory that we have today. Today, we can just say, oh, it's H2O, and you can explain everything that water is based on that. We don't have anything like that for life. So what we're going to have to do is kind of describe it and try and come up with some kind of ideas as to what life is. So here are some of the things that, this is actually from my students, things they came up with. Some of them I will not put up. But some of the more popular ones were it grows, it moves, it dies, interestingly enough. Something's alive if it can die. Reproduces, it uses energy, it evolves, and usually the students who were more in the biology majors would say it has DNA. So that's really specific. And then you can have some fun, because then you can start saying, well, all right, mountains grow. Are they alive? Fire, it kind of moves. It uses energy or uses fuel. It dies, certainly. Responds to stimuli. If you ever have a chance to play around with a plasma ball like this at the Science Center, you'll know that when you touch it, it sort of moves around with you. So that seems to be responding to stimulus, but we're pretty sure it's not alive. It reproduces. Well, if you have a mule, which is the offspring of a donkey and a horse, it's alive, presumably, but it cannot reproduce. It's sterile. And the really tricky one that you can always have a lot of fun with is viruses. So viruses, they have DNA, or RNA. They certainly evolve. That's why we keep getting the cold, because they keep evolving to get past our immune system. The question is, are they really alive? And I sort of fall on the side that not really, because without us, without cells, they cannot reproduce. They actually hijack our own reproductive system in order to reproduce themselves. So I'm going to call that not alive. And we sort of get to this notion that really what we're looking for is something that reproduces and evolves. And if you put those two things together, you sort of get, except for noticeable exceptions, you sort of get the right idea. So how are we going to identify life? Because that's also something that we have to worry about. When you leave tonight, go around and think about life. Really, think about life. It's complex. It's insanely complex. I mean, I work with stars that go supernova. I work with galaxies. And, there's variety in those things, but it doesn't come anywhere close to the kind of complexity and variety we have with living organisms. So we're going to find things that are complex. They're also information, right? We carry the blueprints of what makes us in every single cell in our bodies. So we pass on that information to our offspring, and that information evolves over time. So that's a great way to define life. Unfortunately, it's rather impractical because we don't have the time to sit around and watch things evolve in order to identify them as being alive. So that's not going to work so well. A lot of my students says, well, come on, we'll know it when we see it, right? I mean, we look at fossils and we say, hey, that's alive. That can be kind of subjective. And I'm going to show you an example later on in the talk where that could be playing a part, our subjectivity, what we think life should be. So what we're going to do, at least for the rest of this talk, is we're basically just going to assume that whatever life we're looking for is going to be life like ours. Because we understand, mostly, how we work, and we understand how we influence our environment. And so if we find the same kind of influences elsewhere, we'll say, aha, we found something that looks like it's alive. But a word of caution. And maybe some of you have seen this before. This is a fantastic short story by Terry Bisson. I think that's how he pronounces his name. But in case you can't read it from way back, let me just read the parts here. And it's a play, a dialogue between two aliens who have one of whom has visited the Earth. He says, "They're made out of meat." That's impossible. What about the radio signals, the messages to the stars? They use radio waves to talk, but the signals don't come from them. The signals come from machines. So who made the machines? That's who we want to contact. They made the machines. That's what I'm trying to tell you. Meat made the machines. That's ridiculous. How can meat make a machine? You're asking me to believe in sentient meat. Gets much better, but we'll stop it there. But if you just Google, they're made out of meat, you will find this very easily. Okay, so we're going to talk about life. We're going to talk about meat, which is us. And what are the ingredients we're going to need for life? Because this may give us a clue as to how much life there could be elsewhere. One thing we need is a source of energy. And the reason for this is that life is highly ordered. If you think about everything you see around here, right, the buildings, us, animals, trees, all of that somehow came out of some primordial ocean of molecules, which was very random and has gotten together and created something very ordered. And we grow. We take stuff in and we grow ourselves. We get more and more ordered, despite the fact that some of us may have a little bit more disorder around us to compensate. Any of you who have kids know what I'm talking about. But still, this seems to break the second law of thermodynamics. And you'll hear this a lot sometimes about life, that we break the second law of thermodynamics. And that second law says that disorder has a tendency to increase over time. But we can do that because we're not really breaking the law. That only applies to a closed system. And we are not a closed system. Heat is escaping the Earth, and heat is being bombarded on the Earth, and we get heat from the sun, and we get energy from the sun, and we can use that energy to create order. So whatever life we come across should probably be able to use energy to order itself. We also need a stable environment. We need a way to get the ingredients that we need together, keep them around, and not have everything get clobbered by asteroids or cosmic rays or anything like that before it has a chance to get going. So we need some kind of stability. And just because I used to teach this, I'll say this is not to scale. Right? You all know that, but let me put the version that is to scale. Yeah, it's right there. Might have a hard time seeing it, but there it's right there. Okay, but now I would like you to put on your glasses, if you'd be so kind. This really doesn't have anything to do with life. It's just a really cool movie that I wanted to show you. Okay. And I really want to get this. It's going to make an excellent Facebook entry. Yeah. All right. All right. Let's start this up. So actually, I'm going to hold off for a second. I want you to look at it for a little while. The red doesn't quite come through as brilliantly as it should, and so the effect might not be as good as it could be. Give your eyes a chance to get used to it, and maybe sort of let them uncross themselves and look a little closely, and I'll give you a few seconds to do that, and then I'll start the movie. This was taken by NASA's stereo satellites. These are two satellites that are observing the sun at the same time, and so they can get the 3D perspective, and we can make these fun movies. Here we go. How's it looking? 3D-ish? Yeah, no, yeah. All right. There's a few more after this. Feel free to keep them on if you want, but that was it for this particular movie. So that was just a cool thing. Now let's get back to life. So what do we need for life? So we said we need energy. We need a stable environment. We also need something called a solvent for life like us. Because life like us is molecular based. We live on chemical reactions between molecules. And without a solvent, a lot of those chemical reactions simply can't happen. The molecules that are involved are just too tightly bound to each other, and they can knock together, but they're not going to react. And if any of you have baking powder in your house, okay, baking powder, not to be confused with baking soda, baking powder is actually baking soda, but there's also an acid salt in there, and some cornstarch to absorb any moisture. Because that baking powder sits there on your shelf, basically doesn't really do anything until you add some water. You put it in a recipe. And when you add the water, what you're doing is you're putting the sodium bicarbonate, which is baking soda, and the acid in solution. And the water molecules sort of come in and they pull those molecules, the other molecules apart. And they mix them up, and now they can come together, react, and you get fizz, or properly CO2. And that makes your bread rise or your cakes rise or anything like that. So we need something that's liquid that can act as a solvent. Now, it turns out there's actually several different kinds. But water seems to be a really good choice. And the reason is because, and you'll see this often, okay, well, hopefully you can sort of see this. Water has a very large range over which it's liquid and can act as a solvent. Ammonia also is pretty good, but it actually needs to be rather cold in order for it to be liquid. Same with all these other ones, methane, ethane. Ethane is really interesting because it has a very large range over which it's liquid, as well as water, so it could be a good candidate. But all these guys have a tendency to be very cold, and chemical reactions go a lot more slowly when things are cold, and so it might not be the best way to get life going quickly. The other nice thing about water is you've got soluble molecules, things that actually do dissolve, and then you've got other things like fats and lipids that do not dissolve, and they can actually form membranes and make things that protect the thing that's alive. So that's always a good thing. However, there is one note of caution. And that is that all of that stuff I just showed you was at room pressures, at terrestrial pressures. It turns out you can actually have liquid ammonia at room temperature if you put it under enough pressure. So there could be other worlds out there where the atmospheric pressure is high enough that you could have ammonia as a stable liquid, and you could have ammonia-based life. And this is just a phase diagram of water. And all it really shows is on up here, this is getting low pressure to high pressure. This is low temperature to high temperature. And every point in here will tell you if water is either solid, liquid, or gas. And if any of you have ever gone hiking up in the mountains and you need to boil your water, you may know that you have to boil your water extra long because water boils at a lower temperature at altitude. And that's what you're seeing here. The transition between liquid and gas actually comes down as the pressure comes down. So it's not as simple as some of the textbooks might actually have you believe. There are lots of possibilities. But water has one very, very interesting quality, and that is that it floats. Of all those solvents, it's the only one where the solid phase is less dense than the liquid phase, and therefore you get ice that floats on top of the water. And think for a moment what would happen if that were not the case. Winter comes along, you have a lake, top layer freezes, sinks, kills the fish. Next layer freezes, falls, and basically the entire lake freezes over completely. Whereas in reality what happens with us is we get a nice layer of ice on the top, and it turns out ice is actually also a good insulator. So it can actually keep some of the heat underneath the lake. Everything stays nice and liquid, fish live, and we get to evolve from the fish. So water actually is really interesting in that it is unique to have this property. If there are any chemists out there who know of other really exotic liquids that also exhibit this, let us know at the end, because I haven't been able to find anything. So like I said, we're molecular-based life, and it turns out that we are based on a very simple set of elements. And the biologists call this schnapps. So that's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the bulk of what makes up you and me. Okay, most of us is H, two H's and an O for the water content in our bodies. But we also have quite a bit of carbon, some nitrogen, and phosphorus actually plays an important role in much of our biochemistry. And there's a very good reason why these are the ones that are used. And that is because not only is water unique, but carbon is unique as well. It has 4 bonds that it can make with other molecules. And those bonds are strong, and they're about as strong as the other bonds in the molecule. And that allows carbon to create these very large, complex molecules. Maybe you've heard of this thing called a buckyball. It's basically, this is all carbon. It's a molecule that's entirely made of carbon, very strong. They also make tubes out of this for carbon nanotubes, and maybe there's a future in that. for making extra strong ropes and things. This here is an amino acid called glycine, and it was actually recently observed by a Stardust mission that went and took the contents of a comet's tail and analyzed it, and turns out there's amino acids in there. Amino acids, by the way, are the building blocks of you and me. They build up proteins, and proteins builds up us. Here's a really favorite, tryptophan. You probably have heard of tryptophan. This is the turkey thing that makes you sleepy, although I don't think that's quite right. It's probably more like you eat a lot and you get sleepy. And then just have a look at this thing, insulin, which is extremely important for us. If anyone has diabetes, they know that this is an extremely important chemical to have, or molecule to have in your body. And it just shows you how big these things can get, how complex this can get. And carbon is unique in being able to do this. Okay, so how do we get these things? Let's go through a brief history of us. And I do mean brief. You're going to get more of this from Rocky Kolb, who will be telling you about dark energy and dark matter and probably how the universe evolves. Alan will be telling you more about how galaxies formed. And TJ is going to be showing you all great, wonderful things. And I'm going to show you just a little example of that. So first off, the Big Bang happened. And it gave us some elements, but if you took a chemistry class back then, it would be a lot easier. Hydrogen, lithium, helium, and beryllium, and that's it. You can't make anything heavier than that for technical reasons I won't get into right now, but come back to the other lectures. I'm sure you'll hear more about that. Well, what does give us these more complicated elements that we need in order to make life? Well, we need to wait for stars. And stars shine because they do something called nuclear fusion. Fusion takes light elements, slams them together to produce heavier elements with more protons, more neutrons, and you get energy out of that. The problem is getting these guys together, close enough together to actually have that happen is really hard because these are protons, and protons have a positive charge, and they repel each other. In order to get them close enough so that the nuclear forces can take over, requires incredible pressures and temperatures so that you get these things confined enough and going fast enough that they just slam into each other despite the electric repulsion and do fusion. And that requires something like a star. So here's a picture of a star, and it's got layers, and in the very center you have the kinds of pressures and temperatures you need in order to have this happen. So we need to wait around for stars. And that will get us up to iron, because you can put things together and get energy out of it up until you get to the element iron. After that, it takes energy to push things together and make heavier elements. And in fact, what we do in our nuclear reactors is we actually take large things like uranium and we split them. It actually gives you energy. So it's got two sides, and iron is right in the middle. And what happens is when these stars reach that point of making iron in the center, they essentially turn off in the center. The entire thing comes imploding down, and you get a supernova, which is the stuff I sort of work on. And that's all I'm going to say about them. Except that the energy output of these things is truly incredible. They outshine the host galaxy they live in when they go off. There's so much energy involved that you can now get heavier elements. Basically, it slams these elements together, and you get things like iron, you get the heavier elements, gold, platinum, and all those wonderful things. Anything gold, you guys got gold? That comes from a supernova. There's no other way to make it. And the explosion, as you can see here, this is a picture of the Crab Nebula, very famous supernova explosion. It sends all that off into outer space. And so all these first generations of stars that only had hydrogen, helium, and beryllium, and lithium create the heavier elements, blast apart, send that off into space. The next generation of stars builds out of that material and builds up and builds up and builds up, and sooner or later you get something that's going to give you a planet, hopefully a rocky planet like ours, and the ingredients we need for us. 9.25 billion years after the Big Bang. But it doesn't look exactly like what you would think of as the Earth. In fact, not too long after this, the moon formed when a large planetesimal slammed into the proto-Earth, created a big dust ball, and then that formed into the moon. But for a very long time, for the next 500 million years, you still got these stray bits from the solar system coming in and slamming into the Earth and keeping it very hot, very molten. And it wasn't until about, again, 500 million years after it formed that it cooled down enough, for long enough, that you actually had water accumulate. And those of you who actually went to George Preston's talk learned all about where water came from, so I don't have to talk about it. Those of you who didn't go to George's talk, well, sorry, I'm going to move on. And then time went on, and this is an interesting view of the different geological eras of the Earth, and I like it because it's sort of put around in a circle, almost kind of like a clock. I'm going to make the analogy with a clock in a second, but what I want you to see is that this portion, so you could start to think of this as 0 hours all the way around to 24 hours, and that's today. A good fraction of that here, called the Hadean, very hard for life to get going there. This is when we had the constant bombardment by all this stuff that's left over in the solar system. And then we have the next bit here, and this purple line that strikes all the way around, those are prokaryotes. Prokaryotes. Basically bacteria. Very simple, single-celled things. And they start somewhere in here, almost immediately after the bombardment stopped. Didn't take any time at all. In fact, there's some evidence that it actually even started before the heavy bombardment. So who knows, maybe life got going even before that was over and maybe had a dead end because it got smashed. But as far as we can tell, it happened very quickly and lasted a very long time until you get to here. And that is where you start to get into the eukaryotes, which are cells like us that have a nucleus in the center with the genetic information. Multicellular forms start here. Then you get, this is plants. No, sorry, this is animals. You get land plants, so plants that happened on land, mammals, and us, kind of there, which you can't see because it's too small. So let me put this in a better analogy. If the Earth were 24 hours old, bacteria have been around for 20 of those hours. Multicelled life has been around for 3.3 hours. Plants have been around for 2.4 hours. Animals, just under 2 hours. Dinosaurs lived for 52 minutes before they met their demise. Homo sapiens evolved 4 seconds ago. All of recorded history, literally the blink of an eye, because it's about 0.1 seconds. So usually in astronomy, we try to make you feel small in the spatial sense. Tonight, I'm going to make you feel small in the temporal sense, in the sense of time. But as time went on, things got more and more interesting. This is the only figure in Charles Darwin's book, famous book, On the Origin of the Species. And it shows the very basic idea that you start with life down here, and through evolution, you get branchings that go off. We usually think in evolution in terms of this little thing that slowly evolves into these more complex things and basically gets to us. And certainly one path takes that route. But there are other paths that branch out. Here's a more common version. And we now know that there are 3 basic kinds of things. These are cells that have nuclei, eukaryota. We have something now called archaea, which I'll talk about in a second, and then we have bacteria. And using genetics, mapping out the genome, what we can do is we can compare things and see how similar are they and where did they branch off. And we can say, okay, here's animals, not too far away from fungi and plants and slime molds, right? Close relative, relatively speaking. And we bring them back, and it seems we came from a common ancestor. That's what it looks like. Every form of life on Earth uses DNA or RNA. Okay? Very indicative that we may have come from some thing, one parent organism. Now let's talk about these archaea because they're really interesting. They're kind of like bacteria. They branched off kind of early, and several of them live in very, very different environments. And you've probably heard of these ones. These are hydrothermal vents. This is far, far, far underneath this ocean floor, underneath the ocean surface, about 2 miles down. No light can get down there. There's no photosynthesis down at this point. And when they went down and investigated these black smokers, what they're called here, they were surprised to find an ecosystem down there. It's not an ecosystem based on photosynthesis, like our ecosystem up here is. Right? We basically all eat plants, and the plants get their energy from the sun. Down here, you have what are called thermophiles, and they can live in extremely hot temperatures, and their biochemistry works in a completely different way than ours. They extract energy from the hydrothermal energy coming out from the middle of the Earth. That hydrothermal energy is kept alive by nuclear fission. So this is nuclear reactor life, if you like. It's not based on the sun. Here's another example down here. This is Grand Prismatic Springs in Yellowstone, and this is a hot spring with very, very hot conditions, and you can get bacteria that live in there just happy as clams. So life seems to happen everywhere. Right? It doesn't need very special conditions. It seems to be able to find a niche wherever there's liquid water. But the question is, how strange could life get? And you may have heard recently, just at the end of last year, NASA made this big press announcement, and it said, NASA will hold a news conference at 2 p.m. Eastern Standard Time on Thursday, December 2nd to discuss an astrobiology finding that will impact the search for evidence of extraterrestrial life. And if you read the blogs, everyone said, oh, they found life on Titan. That's what it is. And so there's this cartoon down here. I don't know if you can read it, but these guys are saying, our arsenic-based DNA discovery is cool, but these reporters are expecting life on Titan. Our press conference will be such a letdown. Okay, we need to make it more exciting for them. How do we make an event entertaining? I don't know, I suck at parties. Music, I guess? WikiHow says we should serve cocktails and hors d'oeuvres that fit the theme of our event, which is arsenic-based life. So we're kind of... It takes a minute to get these. This is XKCD, a fantastic webcomic. Arsenic-based life. Unfortunately, that makes you think that this is like arsenic taking the place of carbon or something, and that's actually not what's going on. It turns out that arsenic is very close to phosphorus. In the periodic table, it's just below phosphorus. So it has a lot of the same chemical properties, and that's what makes it so toxic, because it gets into our bodies. It's just enough like phosphorus that we take it in very easily, but it's just enough not like phosphorus to screw up the biochemistry and kill you. Despite this, they found some bacteria in this place called Mono Lake in California, which is really close to Lake Tahoe, and extracted that bacteria, put it in a petri dish, and fed it arsenic-based nutrients. And it seemed to grow in that kind of hostile environment. This created a really big dust-up. A lot of people have come back and saying, oh, you didn't do this right, you didn't make proper controls, you didn't keep out possible cases of contamination, on and on and on and on and on it goes. So to date, as far as I know, there's only one published study. That's the initial finding, and we're going to have to wait until peer-reviewed, published results come out to say yes, no, maybe. Right now, I don't know enough biology to tell you one way or another, but it's really interesting because it does show that life has the ability to take on other aspects in order to adapt to an environment, if this ends up being right. So let me just give you a few big ideas that I've gotten to so far. And that is, it took billions of years for stars to create the elements needed for life, but it began very soon after bombardment stopped. And wherever you find liquid water, you find life. And life seems to be able to adapt to use different kinds of energy, not just solar. So there's lots of possibilities. And so some people say that the search for liquid water is the search for life. That's what you should be looking for. And so that's what we're going to talk about for the rest of the talk. First stop, Mars. Can't do it without Mars. Because, you know, there's just something about Mars. You never hear about the Venusians coming, or the Jovians. Plutonians, no, it's always the Martians. And I think a lot of that has to do with early observations of Mars done by Percival Lowell, who saw canals. And he really did mean canals, as in artificial structures which were taking water, presumably from the poles, down to irrigate farmland. This might have been based on another astronomer's observations, Giovanni, I hope I say his right name, Schiaparelli. And he meant channels, but that was incorrectly translated from Italian to be canals, not channels. Channels you can think of as being natural phenomena, And you really can't blame astronomers for seeing things like this because they were looking with their eyes with smaller telescopes, seeing conditions weren't so great. And it turns out this is a very common optical illusion, that you actually get little point things and your mind connects them. This is the way mind works. Oh yeah, why not? Okay. So I always give this to my students just to say, look, human perception can be a bit of a, can be tricked. So this is where I'm going to ask for a little audience participation. I want you to look at the picture, and I want you to tell me which square is darker. Is it A or is it B? So those of you who think that square B is darker, please put up your hands. Right, and square A? Yeah, okay. Actually, they're both the same color. And usually with my students, what I would do is I would have them cut this out and put them next to each other just to prove to themselves that this is true. But we thought, 3D glasses is one thing, a bunch of scissors, no, it's not going to work. So I'll do it for you. So here we go. Magic of Keynote. Here we go. And ha, look at that. And now I know what you're saying. He says, oh, he's changing the color as he goes along. Okay, so let's do this a different way. All right, back to the beginning. Take that away. Move it. Okay, it's not changing. Not changing. Not changing. Okay, good. All right. Put it back. All right. You believe it now? No. No? Yeah. There's no pleasing some people. All right. Wikipedia, optical illusions, go find it, cut it out for yourselves, move it around, you'll know. Okay. And the lovely thing about this is, even when I tell you about it, it's still there. Right? I can't convince myself that those are the same colors, even when I know there's an optical illusion going on. All right, that was just a little side thing. So, but after we had this notion of Mars, we went back and we observed it with better telescopes. And Mount Wilson actually did observations of Mars. Here is one in 1924 by Edmund Petit and Seth Nicholson, who, I think this is really cool. They basically put a thermometer on the telescope, pointed it at Mars, and found out what the temperature of Mars was. Not quite that simple, but it's about the right idea. And they came out with about minus 70 degrees Celsius. It turns out in the table I was looking at, say, what, 275 Celsius? What? That list should be Kelvin, not Celsius. But anyway, minus 70 degrees Celsius. Another observation, they put the telescope on Mars and took a spectrum of it for, 6 hours. This is Walter Adams and Theodore Dunham. And I believe Walter Adams was the director at the time, George? Right. So I guess director's discretionary time. And did 6 hours and found no water vapor on Mars. 6 hours for seeing nothing, but it's an important result, right? Today, we now know that basically the mass of Mars is 11% the Earth. Average surface temperature is about minus 63 degrees Celsius. And here's the kicker. The atmospheric pressure is about 0.6% of Earth's atmospheric pressure. And that's a bummer because liquid water is impossible on that surface under those pressure conditions. It immediately boils into a gas. So life as we know it cannot exist on Mars today. Okay, you can put your 3D glasses on, have some more fun here. So this was one of the first times that NASA had done the old 3D trick. And this is the Mars Pathfinder mission with Sojourner and looking at rocks. And then we sent other Mars rovers who did even better and went all over the place. And I don't know, are they still even going at this point? I don't even know. I think Spirit's gone. Spirit. Oh, wow. So, they're just the mission that wouldn't end. And we've gotten beautiful vistas of Mars. And they've just gone everywhere and looked at all kinds of things. And I could go on and on and on and on about Mars exploration, but I want to get somewhere. You can have a little more fun. If you haven't been to the JPL open house, you really have to go. They have such cool things. And this is us on Mars, interesting enough. Okay, you can take your glasses off now. One thing we have discovered is Mars it looks like they had liquid water in the past. We see features like these, which look like sedimentary layers. We see features that look like other features we see on Earth, where a violent eruption of water comes out, makes a channel and what's called an apron, and actually leaves behind a cavity, which then collapses because the water's gone. So we see these things on Mars, and we also see them on Earth, and this is actually at Mount St. Helens. Such a thing happened. So there was water in the past. But there isn't now. Here's one more 3D if you want to put your glasses on. Okay, so there's ice, but no form of life that we have seen so far, at least not today. But the fact that there's water on Mars in some form, and there's traces that liquid water existed on the surface, makes us think that perhaps in the past there was liquid water when Mars was a little different. Maybe it had more atmosphere. And you ask the question, if life got started so quickly on Earth, maybe it got started on Mars before the conditions changed. Okay. All right. Remember this guy? So, another news item. This one's a little older, but they thought they found something that looked like bacteria in a Mars meteorite. So this is a meteorite that was knocked off of Mars, probably due to some impact, floated around in outer space for a while, and then landed in Antarctica, where it was discovered later on when the ice melted away. And they found this. And the idea was that this here was fossilized bacteria from Mars. And they ran a whole bunch of tests, and again, this created quite a lot of controversy. And there's lots of arguments on one way or the other as to whether this is alive or not. And we're getting back to the same problem we had before. Will we recognize life? And it's really hard to tell if this is real or not. But there's one basic problem, and that is that these are very small. That's 100 nanometers across, which is a very small dimension. And let me just compare it with another bacteria we saw before, which is the arsenic-loving bacteria. We're going to zoom in on that. And there's our Martian bacteria. And it's small. Now, this bacteria actually is a pretty beefy bacteria. They actually come in a lot of different sizes. And you can get ones that get down to near that size, but nothing quite that small. And we have something on Earth called nanobacteria, which is that small. But biologists are still not sure whether that thing's even alive or if it's just some kind of crystal formation. One of the problems is that it's so small that it's almost the size of its own membrane. So there's not a lot of space left in this thing to hold any bits that you need. But then you say, well, but look at it, right? It looks like life. And this is the question, would we recognize it when we see it? And we've had this problem before. You may remember the face on Mars. All right, so we had this problem, the face on Mars. The thing is, the human brain is really wired to recognize facial features. And we see it everywhere. Okay, let's go back to the real face on Mars. So you look at this, and you say to yourself, wow, that just looks like a face. Also, there's a bad pixel there that looks like a nostril, which doesn't help. So, but then you go back and you look at it with higher resolution with the Mars Global Surveyor, and you see that, okay, face of Mars, not so much, not really. 3D, it's the last one. Enjoy. By the way, you're allowed to keep these, take them home, use them on the web whenever you find a 3D image. Looking good? Okay. You're convinced? All right. How about this one? There's another one on Mars. All right. Well, hey, why Mars? Let's go to Earth. Go to Google Earth. You can find all kinds of nice things. Do you see this one? Okay, maybe we need a little help. Here, how's that? Okay. Okay, so that's it for the inner solar system. The 4 terrestrial-like planets are rocky things. We've got Mercury is too close, no chance. Venus, also too close. Its atmosphere is too thick. It's too hot. Liquid water can't exist, so that's no good. We've got Earth. Well, we know that works. And then we've got Mars, which was too cold, too small, cooled down too quickly, lost its atmosphere, whatever happened, it didn't work. So what do we got left? Well, we can go to the outer solar system. And I'm not going to spend too much time on this. Europa is a moon of Jupiter. So Jupiter is not really a great place for life as we know it, but its moon could be. Turns out that the surface is very smooth, very few impact craters, which tells us that the surface is very new or constantly being replenished. It's got lots of cracks. And so the idea is that there's actually a liquid ocean underneath here. And whenever a crater or a crack opens too wide, water spurts out, resurfaces, the Zamboni goes across, and you get a nice flat surface. Then we also have this new guy, new kid on the block, Saturn's moon Titan. Now, this is very far away, no liquid water, but it's got an atmosphere, and an atmosphere is actually has more pressure than Earth's atmosphere. Except it's very cold, but you can have liquid methane. And Cassini flew by, took some radar pictures, and found lakes. As far as I know, this is the only other body in the solar system that has liquid lakes on the surface, which is incredibly cool. I mean, this just blew me away totally. So, could there be life in there based on a completely different chemistry? It's very possible, and we'll have plenty of data to find out. Okay, so the last few minutes, I'm just going to say there's several possibilities within reach for us right now. The conditions on early Mars may have been hospitable to life, at least simple life. Europa could have life under the ocean. Titan has lakes of liquid methane. This could be a completely different chemistry. That'd be cool. What about life out there beyond the solar system? Well, now we're in the realm of astronomy. Great, fine, great. Away from all this other stuff. We can't go there. It's going to take too long. So we have to look at the light that comes to us from those planets and use telescopes. And we can use lots of different telescopes. So I'm going to talk a little bit about planet hunting. This uses a technique. It turns out that when a planet goes around a star, they're in a gravitational tug-of-war. And planet goes around, but the star wobbles back and forth as well. It's kind of like if you go around with somebody and you twist around, you actually go around a common center of mass. And when we look at the spectrum of this light, basically break it up into a rainbow, the elements in the atmosphere of the sun or the star will give us these lines. So let me show you the animation of what happens. There's a little bit of audio help. If you've ever heard, it's a bit too loud. That's the sound of NASCAR cars going by. And you hear the, that's the Doppler effect. And it happens for light too. So what happens, you can see, the spectrum shifts back and forth as the planet goes around. Okay? We're doing this on Magellan now. So Paul Butler at the Department of Terrestrial Magnetism, Jeff Crane, Steve Scheckman, and Ian Thompson have put together an instrument that is specifically designed to measure that spectrum, that prism of light, look at those lines and see them wobble back and forth. But to get to the really small, interesting Earth-like planets, you have to measure very small wobbles back and forth. So you have to look at that spectrum in much more detail. That's it. In fact, they stretch it out so much it won't actually fit across the CCD image. So you have to make it through some clever optics, do multiple lines and scans and get the whole thing in on one chip. And I'll just zoom in a little bit on one of those. And you can see there are all kinds of lines in there. But in order to measure this with exquisite accuracy, they also put the light through what's called an iodine cell, which adds artificial lines where we know their positions extremely well and can compare the stars' lines and see them wobble back and forth compared to the ones that stay fixed in the instrument. So that's stuff that's going on right now. Another method of getting planets, of finding planets, is called the transit method. And that is you wait for the planet to go across the face of the star, if the geometry is right, and you see the light dimmed by a tiny little bit. This is best done from space. So we now have a mission called Kepler, which is now going and measuring these transits. And I'll just give you an idea. Here is the field that Kepler is looking at. It's not looking at the whole sky. It's looking at a very specific part. There were 3 known planets in there, and now we know this many planets in there. Isn't that amazing? And we're now starting to know more. And the interesting thing about the transit method is if you saw the dip, the shape of the dip gives you an idea of how the size of that planet is and other things. And so now we're actually finding this is size, and this is how long it takes to go around the star. This is where they first started. The easy stuff, the big planets and the ones that go around quickly. Over time, you get more of them because you now have more time to look for the slow orbits and slower orbits. And now we're actually getting down into the really interesting bits. Okay. So I'm running out of time, so I'm just going to go to the punchline. Yeah, let's go back. So I've talked a lot about a lot of different things. What we'd really love to do is take one of those planets, isolate its light, and see if it's got the signs of life in its spectrum, maybe signs of oxygen, water, stuff like that. And that's going to be the next generation of telescopes. And that could be a talk all on itself, so I don't have time to go there. But you're probably asking yourself, talking and talking and talking and talking. The question remains, is there life beyond the Earth? Okay, well, I'm going to tell you that simple life began very quickly on Earth. And that is the one thing that convinces me that it's easy to do. It didn't take billions of years of stuff just lying around before something happened that made life. It started really fast. Kepler has now found 1,235 planets. That's a lot. If you extrapolate that to all the stars that you wouldn't be able to detect this with because the planet doesn't go across the face of the star because it's on the wrong angle, you get basically 50 billion stars in the galaxy. Oh, let's go a little bit further. More extrapolating, that's 5 billion trillion in the observable universe. And unfortunately, that's not counting these new galaxies we know about now called dwarf galaxies. I just counted up the big, huge galaxies like ours. So there's even more than that. That's a lower limit. So the question is there other life? Absolutely. Is there life in our galaxy? I'll bet my house on it. George, we'll put my house on your ceiling. Got the bet. But you're still probably not convinced. You're not satisfied because what we really want to know about. And I tried to put a little something for everybody in here. Is there intelligent life out there? And that is a really, really tricky question because defining life is one thing. Defining intelligent life, that's a whole other kettle of fish. Personally, I think it's probably very rare. And here's why I think so. So I showed you that tree of life before. This is a more realistic tree of life, by no means complete. Here are the bacteria. Here are those archaea, the extremophiles, the ones that live in the bizarre. Here's everything else. I'm going to zoom in here a little bit, so you can't see so well. Where are we? We are there. Homo sapiens. Sapiens. So we branched right here. Next one over is Pan-troglodytes. Does anyone know what that is? Chimpanzees. So our closest branch-off relative is a chimp. These are things that live today. We're not counting stuff that died out because of extinctions. Oh, sorry. Oops. Back. Go back. Okay. Oh. Okay. Well, anyway, the point I wanted to make was it doesn't seem to me like intelligence is an evolutionary imperative. Sure, one line, if you follow it, went to intelligence, but there's a lot of other lines in there. Bacteria have been around for a long time and didn't have any need to develop intelligence to stick around. The dinosaurs were around for a very long time, and as far as we know, did not develop any kind of technology. Okay? So it seems to me that life itself is probably ubiquitous. But intelligent life, I think, is much, much, much more rare. And I don't think we're going to find any very soon. I'd love to be wrong, but I suspect it's going to be a very long time before we find anything that looks like intelligence. So anyway, that's the end. I did want to, I got to go through this again, of course. Chimps, us. Just a couple of thanks to TJ Cox, who will be giving a talk in 4 weeks, April 18th. He pointed me to some of those cool simulations that you saw. Thanks to George Preston, who actually gave me a little bit of history and came up with the Mars connection with Carnegie and the telescope. And to all my Carnegie colleagues for leaving me alone for the past week to do this. In fact, the most intimidating thing about doing this talk was that as soon as anyone came to my office and saw me working on this, they would say, oh, I'm sorry, you got to do this, and they would leave. It doesn't happen for any other reason. So those are my thanks, and thank you all, because whether you are friends of the observatories and have given money, or if you pay your taxes, some of that money goes to pay for my salary. And if it weren't for you, I wouldn't be able to get to do this really cool stuff and talk to you about it. So thank you very much.
I'm sure we have a few questions. We have time for a few questions. Speak loudly, please, so you might want to repeat the question.
Yeah.
There you go, sir.
So the question was, does Mars have enough gravity to hold on to a thick enough atmosphere to keep liquid water? Is that the question? So there have been lots of ideas about terraforming Mars. So Mars has two problems. One is it's smaller, so its gravity is lower. The other problem it has is it doesn't have a magnetic field. And the Earth does have a magnetic field. And I can show you a little picture, maybe, if it doesn't take too long. And it's thought that perhaps one of the reasons Mars lost its atmosphere is because it cooled down so quickly and it lost its magnetic field that it no longer is shielded against the, it's no longer shielded against the sun's solar wind. So what you can see here is here's a picture of Earth and its magnetic fields, and it sort of creates this shield against the solar wind. And so certainly the idea is that if we could get something on Mars that would start creating greenhouse gases and create enough of that to get the atmosphere thick enough and the pressure high enough, then yeah, we could have liquid water. The question I have, and I'm not quite sure about, is whether or not that would last, if it's a sustainable thing. You'd probably have to keep having to push greenhouse gases into the atmosphere. Because the other thing is, Mars does not have any volcanic activity at the moment, which is a really great way to get greenhouse gases back into the atmosphere. So it's possible, and it certainly has a little bit of an atmosphere. And Titan, which is even smaller than Mars, has an atmosphere that is as high pressure as Earth, although it's colder, so gas doesn't move around quite as vigorously. So I believe that there are ideas for terraforming Mars, but it's going to be a long time before we take on anything like that. Yeah. So the question is, what creates magnetic fields, and are there any planets that have them? We believe that because the Earth has a liquid iron core that spins, that creates a dynamo, which then produces a magnetic field. So in the case of Mars, if the interior cooled down is no longer molten, then it can't spin up and it doesn't create a magnetic field. Jupiter has a crazy magnetic field that is very, very strong. And in fact, one of the reasons we know that Europa, or one of the reasons we suspect that Europa has a liquid ocean underneath it, is that when Europa passes through this magnetic field, it actually alters it. And the easiest way to explain that is if there is a liquid saltwater ocean, which is a conductor, and that would allow for changing the magnetic field of Jupiter. But yeah, other planets definitely have magnetic fields. Yeah. Scott?
When you say an atmosphere has pressure, what's the difference between that and gravity, or how much a planet sucks?
How much a planet sucks? So when the question is, what's the difference between pressure and gravity?
Yeah.
Well, certainly so if you think about water, when you dive, if anyone's gone diving or swimming, as you go lower down, okay, you feel more and more pressure. And that's because there's more and more water on top of you pushing down on you. And so the more gas you have in the atmosphere, the more there is there, the more there is to push down on you, and the more the pressure is increased. In fact, Venus has so much atmosphere and so much pressure that if you were to move your hand around in that atmosphere, if you could survive the 800 degrees, it would be like moving your hand through water. It is so thick. I mean, that is really high pressure. So does that answer your question? So you need gravity. A planet with a stronger gravity has an easier time holding on to a large atmosphere, but you can still get atmospheres on small things. Yeah. Yeah. Okay, so the question is, what is your question about that? Sorry. So the question is, will the James Webb Space Telescope have enough PR because it doesn't have an optical component? I think it's going to have an optical component. Yeah. Right, so it stays away from the ultraviolet light, and it has visible, but its strength is it's going to go into the infrared. And in fact, it's going to have a almost better PR because it's going to be able to see more than the Hubble did. And one thing, which I didn't get a chance to sort of show, which I now can because someone's asked the question. I love it when that happens. If you want to actually image a planet, you've got a problem. Stars are really bright, planets are very dim. This is Fomalhaut, which is a very bright star. But what they did with Hubble is they went down into that little red square there, blocked out the light of the star as best they could using what's called a coronagraph. And if anyone is near the lights, if we could just bring them down just a little bit so you could see this. hiding in all that glare, when you took the light out, you could actually see a planet, thanks, and that planet moved. So it's an imaged planet. Unfortunately, the bad news is, there's the orbit of Pluto for scale. So it's way out of there. Okay. But the nice thing is, in infrared, this is optical. In the infrared, that star isn't as bright, and the planet is brighter. So the contrast ratio is going to change. And that's why using infrared is probably a great thing. And we had some plans to do this, but those missions so far are indefinitely deferred. That was PTF and SIM. Yeah?
On the remoteness of intelligent life, is there any way to estimate, or has an estimate been made of the evolutionary path that failed to produce intelligent life here on Earth?
Oh, okay, so the question is has there ever been a calculation to determine the number of times that life did not become intelligent? I think it's all of them, except us.
It's a question as to the remoteness of the
So, it seems, okay, again, this is outside my field of study, so I don't know exactly if someone's actually computed a probability is what you're looking for. You're looking for like a number. For me, when I look at this, it's really hard to tell because we can go and we can look back and we can say, oh, well, obviously, look at all the things that happened. We became intelligent because the climate was changing, and of all the different hominids, we were the ones that could think the most and adapt to the conditions, and therefore it must be something that happens. But then you go and look at all these bacteria that have been lying around, being bacteria, basically the same kind of bacteria since the world began, didn't have any really need to become intelligent. It's hard to put a probability on that, I think, without a deeper understanding of what drives intelligence, what drives complexity, more importantly. What happened such that things like bacteria, and all of a sudden a branch went off that was something more, multicellular life. Is that something that has a definite natural selection imperative? Or is it just a fluke that it just happened? And it seems to me that something just happened. And you just look at all those paths and you could just count them all up and find out what the path for intelligence is, and it's very small. Yeah? So I guess the comment is that we've got all this extra CO2 on Earth. Why don't we just ship it off to Mars and start the greenhouse effect there? There's a slight energy problem with that. We were just having a conversation today at lunch where one of our colleagues was sort of feeling kind of guilty about eating Chilean blueberries from Trader Joe's. And so when you move something from one place to another, that requires energy. That energy will produce, in the case of fossil fuels, will produce greenhouse gases. The energy requirements to send something to Mars are very large. And I don't think you'd win out in the end on that one. I think you'd end up making the problem worse. But it is interesting that maybe we could send something, remote probe of some kind, that could start something going that might reduce some of the CO2 that's bound up in the soil or something like that. That's for many future generations. We got problems right now that we got to deal with on Earth.
Okay, I know we have a lot more questions. If you have questions, feel free to come up and ask Chris. He'll be happy to hang out. His family ran off. So you have no reason to go home.
That's right.
And join us in 2 weeks for Rocky Cove. Thanks for coming out.